Hello, let's talk about torque. So, we've learned about variables of rotational motion. It's been like a week or two. Um, and one of the things we learned about was angular acceleration. Uh, and we talked about how the angular components were analogous to the linear components. So how angular acceleration works a lot like linear acceleration. Um, we also learned way earlier in the quarter that a force acting on an object causes acceleration. But what causes angular acceleration? That is the topic of this lecture. Let's start by taking a look at this situation. We have a door and we're applying these different forces to it to try to get the door to open. All of these vectors are the same size, but they either act at different points on the door or they act in different directions or at different angles, which I guess is different directions. So I want you to pause for a second before continuing this and think about which of these forces would be most effective in opening the door. Maybe even go try it on a door right now. Push near the hinges, like force 4 here. And then push all the way at the end and kind of push in the different angles. So push along the door, push perpendicular to the door, push at an angle from that, and see what works best for opening the door. And if you don't want to physically get up and try it, just also think about it. Think about where most doors have their doorknob. And what it might be like if a doorknob was near the hinges, like where force 4 is applied. Or what if it was in the middle of the door? Because some of those exist. They're cool looking, but we'll get to it. So, opening a door is actually causing a rotation. The hinge is the axis of rotation, and we apply a force that causes the door to rotate around this axis of rotation. So knowing that this is how a force can cause rotation, we can establish some factors that impact the ability of a force to cause a rotation. So first, it depends on the magnitude of the force. That one is more straightforward. So just like for linear motion, um, if you want to see like cause more motion from applying a force, you apply a bigger force. Like that makes sense. But that's not the only thing when it comes to rotating. It also depends on where the force is applied in relation to the axis of rotation or pivot point or hinge in the case of a door. So in this example with the door, 3 of the forces act at the same distance from the hinges. They all act at the like very far edge of the door. So that part is the same for all of them, all 3 of those. But then force 4 acts much closer to the hinges than the other 3. And then there's one more thing that matters when it comes to applying a force that causes rotation. It also depends on the angle the force is applied at. So if you paused at the previous slide and tested this out on the door, you should at the very least have been able to see how the distance from the hinge affects things. It was probably really hard to try and open the door by applying a force so close to the hinges. So it should have been clear how the distance from the axis of rotation, the hinges in this case, changes how easy it is to get the door to rotate. You could have also recreated force 2 where you push along the door and And you might have seen that, well, that doesn't really do anything. It doesn't really make the door turn. You can try this with a pencil. So when I am doing stuff with torque, I like to refer to my writing utensil usually. So what you do when you're doing that is you pinch where your axis of rotation is. So I just pick one end. And then you just try to kind of apply the force at the area that you expect. So like if I was applying force for, I would get really close to the axis of rotation, and then I would pull up, or you could push up, I guess. But then if I'm going for force 2, I would go all the way to the end. So I'm trying to make it not blur out what I'm showing. And then push. And you can see that's not cupping rotation. I mean, my hands are moving, but that's me. But if instead I did it like force 1, where I kind of pull up, yeah, that's definitely going to cause rotation. And then if I sort of try and do it at an angle, that will still cause rotation. So if you didn't want to get up and try it on the door, you can also use whatever you're writing with. So it's clear that forces 1, 3, and 4 will potentially cause rotation, although like some of those, well, forces 1 and 3 will do a better job than force 4. But force 2 is not going to cause rotation. And again, you can test that again with your pencil or what have you. Oops. So this look at how effective a force is at causing an object to rotate. This is called the torque. And it's given by the symbol tau. We have a wrench here as an example, and for the wrench, the pivot is at the end, like where the nut is, and also where the label pivot is. And then the force is applied at an angle at the end of the wrench. And you can see it's also broken into components, a parallel and perpendicular component. And we'll get to that here. So in general, torque is given by this equation R, which is the distance from the pivot point, times the force, times the sine of the angle between the force and what they call the radial line, which is really kind of just like the distance, a line actually from the pivot point to where the force at. So it's labeled R on the slide. Let me see. Yeah, that's what counts as the radial line. So yeah, the force is applied at an angle phi from the radial line. And what we're looking for is the part of the force that is perpendicular to the radial line. That is the part of the force that causes a torque, that causes rotation. Because we saw with the pencil, if we push or pull along the radial line, no rotation happens. But if we are perpendicular, yeah, rotation does happen. So only the perpendicular component causes torque. The parallel component does not cause torque. It does not cause it to rotate. If a force, like if all of the force is applied perpendicular, that is going to cause a bigger torque than, for example, if only a portion, or like if the force is at an angle, so that only a portion of it is perpendicular. So the torque is 0 if the applied force is 0. If it is applied at the pivot point, that one's a little harder to see, but if I kind of try to recreate it with my pencil, that's not, I'm like tugging on that, that's not doing anything. And that's not even like at the same pivot point to be at the pivot point. But yeah, no rotation can happen if the force is applied to the pivot point, if the force itself is 0, or if the force is only along the radial line, only parallel or anti-parallel to the radial line. Yeah. And if you ever forget, if you're ever like just have the equation and you can't figure out which way's the best way, just plugging in the angle. So like sine of 180 degrees or 0 degrees is 0. So that will remind you, oh, the torque is 0 in that case. So just an extra tool. So let's go back to our door. If we assume all of these forces have the same magnitude, which it looks like they do, the only things changing are the distance from the axis of rotation and the angle. So force 4, as we've talked about, is applied closest to the axis of rotation, the hinge. So it won't supply as much of a torque as force 1, for example, which is applied at the farthest point from the axis of rotation. And then force 2, as we've talked about, acts along the radial line, so it doesn't provide any torque. And at this, in this version, the angle is 0 degrees because we would think of the radial line as pointing out here, and there's no angle between them, 0 degrees. But if it pointed the other direction, then the angle would be 180 degrees. That would still be 0 torque. And then force 3, the part of force 3 that is going to apply torque is just this perpendicular component, which we can see that perpendicular component, that's smaller than force 1. So force 3, the torque it causes is going to be less than the torque caused by force 1. So we can, as we saw on them like 2 slides ago, we define the torque as RF sine of the angle between them, but in a description of a problem, you aren't always given the angle between the force and the radial line. Like you might be given a different angle, and in that case, it's fine to either take the perpendicular component of the radial line or the perpendicular component of the force. So, and what I mean by that, for example, is here. So here's the direction of the force, right? And it's at an angle phi from the radial line, which, okay, they gave us the angle, so it's fine. We don't have to do any fancy work, but let's say we don't have this angle. We have some other angle. And it makes more sense for us to get the perpendicular component of the radial line instead. And perpendicular here means perpendicular to the direction of the force. So, and I'm gonna show you an example where we can look at it both ways. But just like we might pull the perpendicular component of the force, we could also pull the perpendicular component of the radius. Because again, it just depends on the problem. So let's look at this problem and then we'll work on it. So Louise has a 20 centimeter long wrench to tighten a nut, turning it clockwise. The wrench handle is tilted 30 degrees above the horizontal, and Louise pulls straight down on the end with a force of 100 newtons. How much torque does it exert on the nut? Okay, let's take a look at this. Okay, so we have a nice diagram for us that indicates what exactly the situation that's being described. And what we can see, let's use a couple of colors. We have a force that acts straight down, but the wrench itself is at an angle of 30 degrees. So this is a place where we don't have the angle between the force and the radial line. We have a different angle. So what we can do is one of 2 options. So if first, let's look at just this option. So there's our radial line, there's our force, and we know this angle. We can find the perpendicular component of the radial line to find the torque. And so our perpendicular is our cosine theta, because this is adjacent to the angle. So that's one way we could do it. Another way we could do it is if we start in the same spot with our radial line and our force going straight down, and if instead we get the perpendicular component of the force. So this is force perpendicular. There. So this also is theta. So in this situation, it works out like if you're getting a perpendicular component for either one. But the perpendicular component of the force is also cosine of theta. But this is just an example where I would do it this first way. With this, that way you don't have to worry about like what is the angle here. You can just based on the information you have, find the perpendicular component of the force. And then now that we've done that, let's just get the number. So we are going to do the torque equals the perpendicular component of the radial line times the force. And that is RF cosine theta. And we plug in our numbers, 0.2 meters, 100 newtons, and cosine of 30 degrees, that's our angle. And we get a torque of 17 Newton meters. That's the units of torque, by the way, is Newton meters. It's just two variables combined, nothing special. But yeah, so that's that example. Now let's do another example. This time, Ryan is trying to open a step door. He pushes at a point 0.75 meters from the hinges with 240 Newton force directed 20 degrees away from being perpendicular to the door. In this case, it's a door, so the pivot point is the hinges. And we want to know what Ryan's torque is. So let's draw the situation. We don't actually know how long the door is, but that doesn't affect our ability to solve it because we know what we really need is how far the force is applied from the pivot point. And then let's say it's here, and that's the perpendicular, because here's our radial line, that's the perpendicular, and then it's at an angle 20 degrees from being perpendicular. So, and this is the force. Okay, so in this case, I mean, they gave us the angle, so we can figure out what the perpendicular component is. We can figure out what the perpendicular component of the force is, and that's just going to be cosine again, because this is adjacent to the angle we're given. And so the torque is the radial line times the perpendicular component of the force, and this is 0.75 meters times 240 newtons times cosine of 20 degrees. Let's see if I can find where this one was. Yeah, so this one is 169 Newton meters. Much bigger, but in this case, the person is turning a door and not just a wrench. But yeah, like not overly complicated when we just have the one force that we're looking at. Okay, let's go back to the slides because there's just a little bit more that I want to talk about. Okay, so now let's say you have the same long thin rod, like a long thin rod, and you want to rotate it about two different axes. One would be along the rod, so just kind of spinning it, like how you would think of us spinning it. And then the other one is perpendicular to the rod, so that's more like this. Okay. You'll find, and also maybe even just you saw from me doing it, that it's a lot easier to rotate along the rod than perpendicular to it. And this is because something that we refer to as the rotational inertia is different. between the two cases. So the rotational inertia depends on the axis of rotation itself, which makes sense. We changed the axis of rotation, that changed in the situation, and on the distribution of mass relative to the axis of rotation. So when the axis of rotation was along the rod, all the mass of that is really close to the axis of rotation, right? Like, yeah, it's not very far. But then if we look at this perpendicular version, well, all this mass out on the end is very far from the axis of rotation. And then some of it is really close. But yeah, there's a lot that's really far. And so what that tells us is that the rotational inertia is bigger for the situation where most of the mass, or at least a good amount of the mass, is far away from the axis of rotation. And it's working along that same principle as the torque, where if our force is applied close to the axis of rotation, then it's not going to cause as much torque. It also means we don't have as much rotational inertia. And just to tie rotational inertia to something we're familiar with, linear inertia is another word for mass. And mass, we know, doesn't change values depending on the direction of motion. But rotational inertia does depend on the axis of rotation, because it's not just the mass, but how the mass is distributed around the axis of rotation. Yeah. So more rotational inertia means more resistance to rotation. Just like mass is a form of resistance to motion, like the heavier something is, the more mass it has, the harder it is to get it moving or stop it moving. The bigger the rotational inertia, the harder it is to get something to start rotating or stop rotating. Same idea. And the only difference between rotational inertia and linear inertia or mass is that it's not just the mass itself that matters, but how it's distributed around the axis of rotation. Yeah, so that's where we'll leave it for now. We'll talk more about rotational inertia, but I wanted to introduce the concept here, and yeah, we'll come back to it soon.